Matter of fact, no matter where I am on the sphere, the area vector at where the electric field comes out will be in the same direction as the electric field.
Because it's a sphere.
Yes, definitely. Well, since my electric field magnitude is the same everywhere, the dot product basically goes away because no matter where I am on the sphere, my area vector and my electric field are in the same direction. I end up with E. Try that again. The magnitude of my electric field times the sum of all the little areas there. And if I add up all these tiny little bits of area over the entire surface of the sphere, what do I end up with? And what is the surface area of a sphere?
Pi r squared.
Area of a circle.
4 pi r cubed.
If you go to cubed, you're now talking about a volume.
Is it 4 pi r squared?
It's 4 pi r squared. So this becomes my electric field magnitude times 4 pi r squared. And my electric field, well, it's just KQ over R, so K, so Q over R squared times 4 pi R squared. And my R squareds cancel out. So I'm left with 4 pi K sub E Q. So no matter how large this sphere is, my electric flux is the same. And if you think about it, what's going on here is that as I get further out, in essence, I've got a bigger area, but my electric field gets watered down in a sense. Let's take it one step further, because that's cluttered. We can make it easier. Remember that K sub E is equal to 1 over 4 pi epsilon sub naught. Just Coulomb's constant, or the electrostatic constant, and epsilon sub naught, the permittivity of free space.
What? Huh?
Oh, this is the permittivity of free space. Permittivity is a measure of how a medium reacts to an electric field.
So is that like a E with a zero?
It's an epsilon with a subscript 0.
Okay.
If it's just epsilon, it's the permittivity of the medium of whatever material it is. With the 0 there, that's the free space. It's sort of that base value. It is epsilon is equal to epsilon sub naught is roughly equal to 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. So, since my electrostatic constant is equal to 1 over 4 pi times this thing called permittivity of free space, and again, this is an epsilon, this is not an E.
Then 4 pi's cancel out.
And what we're left with is Q over epsilon sub 0. Now, we went through all of that, came up with something simple. I'm going to now generalize it. This is we derived it for one specific case, however, it does hold universally true. that if I take my electric flux through a closed surface, CS for closed surface, it is equal to the charge inside divided by epsilon sub 0.
What is the IN?
Pardon?
No, what is the IN?
Inside.
And
It's the Q inside, it's a closed surface, so it's the charge that's inside.
So, you're saying that even if the sphere got bigger, it wouldn't change the electric flux?
That is correct.
Wait, and the charge inside is the same at every point inside the thing?
No, it doesn't have to be.
Okay.
So if I take oh, it doesn't erase that way. So if I take some strange shaped three-dimensional object, it is closed, and I put a 1 picocoulomb, we'll keep it 1 picocoulomb charge inside here. I have the electric field lines going out all over the place here. It would go out and go back in, then go back out again. But the total flux through this surface, no matter where this charge is inside, the total flux, the electric flux, I should say, because we'll deal with another kind later on, is going to be the charge that's inside, 1 times 10 to the negative 12 coulombs, divided by 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. And so we end up with approximately 0.12 Newton meter squared per coulomb. If someone else actually works out 1 over 8.85, let me know what it is.
So that number is equal to the electric flux at any point around.
Through the entire surface. It's the total electric flux through the entire surface.
Alright, so like if you had something that could measure it, you just, any point on that would be the, let's just say 1.2 or 0.12. Anywhere on the surface of whatever.
You
that
say
is.
anywhere on the surface, it's not, it's the electric flux here, plus here, plus here, plus here, if you add them all up.
Oh,
Everywhere.
it'll equal that number.
Yeah, that is the total.
It's 0.113.
113? Okay.
And if you stuck another charge in there, then you would just,
So here, I'm gonna take a negative 1 picocoulomb charge. What is the total electric flux through the surface now?
0.
Yes, because the total charge inside is 0. If I made that a positive 1 picocoulomb charge, the total charge would be, or sorry, the total electric flux would be
0.226.
in those units.
okay, that makes sense.
So if you get some strange shape and I throw a charge into it, it's like Gauss's law test. All right, so this is known as Gauss's law of electricity, or Gauss' law, depending upon how you feel about putting the apostrophe S after an S. Gauss's law of electricity. There is, of course, a Gauss's law of magnetism.
Is it the same person?
Yes. There's the joke. We'll put a question mark next to the word joke. The greatest father-son mathematics pair ever. Gauss and his father. What did his father do? It doesn't matter. It's like a pair of brothers who've hit the most home runs in the baseball. Well, it was Hank and Tommy Aaron. Hank Aaron hit, 700 and something, Tommy 30. Of course, it's been passed now. I don't know who has the record now. Is it Seiko?
Bonds.
Bonds? Barry Bonds, okay. So now it's Barry Bonds, and if he has a sibling, whoever is sibling. Now, let me connect it with something that will keep showing up again and again. There are four major rules here. There's Gauss's law of electricity, Gauss's law of magnetism, what will become Faraday's law, or sometimes I refer to it as Faraday-Lentz's law, and the Ampere's law with Maxwell's correction. Taking these four basic rules, Maxwell uses that to come up with deriving the speed of light, which we will get to. At some point, Maxwell did not do this, but at some point someone referred to these four equations as Maxwell's equations. This is the first of Maxwell's equations. So you might want to make note of that because the other three will come up. Actually, we'll do the next 2.5. We'll do some other stuff and then come back and introduce Maxwell's correction to round it out. And then we will use that to derive the speed of light.
So that's gonna be like our conclusion, to know the speed of light.
Well, to me, the conclusion is once we've derived the speed of light, there are some implications from it, and that leads into special relativity. That to me is.
So, Gauss's law of electricity is also Maxwell's equation.
The first, well, it's not like Newton's laws where there's a first, second, and third. This is generally the first one derived, but this is one of Maxwell's equations.
Made by.
Gauss.
Okay.
Yeah. Again, Maxwell did not call them Maxwell's equations. So he was not that arrogant, although given physicists, he could have been, but he was not. No, he actually has some modesty. When he derives the speed of light, he actually derives the speed of an electromagnetic wave and concludes, well, because this number is so close to our experimental speeds of light might be an electromagnetic wave.
Maybe.
Maybe. All right, questions to hear? Did that satisfy your need for electric flux? Okay. So look at a test question a while back where I had a sphere with a charge stuck in the middle. And what's the electric flux at the surface? And then the sphere falls and the charge rattles around somewhere inside. What's the electric flux now?
It should be the same.
It is indeed the same.
I'm guessing a surprising number of people missed that.
A surprising number of people decided to try to derive it, which
Took them an hour and a half.
even with calculus, it is not an easy derivation. If it's not directly centered and I got some nice symmetry going on. I did do a derivation, I don't know if I posted it for 152, but there's a derivation out there, so I can, if I don't have a link to it in Blackboard, I can give you a link and you can just rejoice in that derivation. Done all that. All right, let's exploit this. I have a line of charge here and a marker that I meant to throw on the ground. Wow.
Even the marker off the box.
I have a line of charge. A line of charge with uniform linear charge distribution. Linear charge distribution or density. I want to know what is the electric field at this point, a distance r away. Now, with calculus you could derive it, but since you refuse to want to do calculus, most of you. I know that I have an electric field, so from this tiny little section right here, I have an electric field going in that direction, assuming that it's a positive charge. If it doesn't specify, just assume it's positive, and if it's negative, that means when you plug into the formula, the minus sign will show up and it's the other way. So this has an electric field in that direction, this has an electric field in that direction, this has an electric field in that direction, and so on. And so we have to somehow add all of these up. If we were doing calculus, we'd just do an infinite sum, in other words, an integral, but we now have Gauss's law. So with Gauss's law, what I'm going to do is I'm going to create a fictional closed surface. This closed surface does not actually exist. It's known as a Gaussian surface. A Gaussian surface is just a virtual surface. It's a make-believe surface that is used for convenience. So I'm going to create this Gaussian surface that's a cylinder. More specifically, a Gaussian cylinder that has a length L and actually I should put it down here, and a radius of R. That's not too many lines. Now, I know, thinking through it, I know that this point right here creates an electric field going into the fourth quadrant. I'm going to have another spot over on the right-hand side of that point, which will have an electric field going into the third quadrant such that the horizontal components will cancel out. For every point here, I got another point over there, which will cancel out horizontal components. So I know that my total electric field has to be away from the line. Known as argument by symmetry. So, if I think about the cylinder, I have an area vector pointing off to the left over here, area vector pointing off to the right over here, and then on the main barrel, I've got it pointing in, perpendicular to the surface. Over here, my area vector is going that way. My electric field is going away from the line. So what is the flux through the end cap? My area vector is going that way, and my electric field is going this way, anywhere around on that circle.
Well, it should be the
Zero.
hypotenuse of that triangle?
No,
Be zero.
zero.
Wait,
Perpendicular, dot product.
So there's no electric field lines going through it, the area,
Right,
so that means it's zero.
yes. Okay, that works. Okay, that's what I wanted. Just hold it. All right. So my total electric flux is going to be equal to the enclosed charge divided by epsilon sub 0, which is going to be equal to my electric flux through the left cap plus the electric flux through the right cap plus the electric flux through the barrel, whatever you want to call it, the annular cylinder. I know that's 0. and that's 0 for the reason they spoke. That it is on the end caps, my area vectors are pointing parallel to the line, my area electric field is perpendicular to the line. So E perpendicular to A. So we just have this barrel here. I know that my electric field anywhere along along the barrel has to have the same magnitude. Because it's an infinite line, because of symmetry, there's no reason for the electric field here to be any different than here, or here, or here, in terms of magnitude. So this is gonna be magnitude of my electric field times the area of the barrel, which is 2 pi r L. That's just surface area of the side of a cylinder.
Now, is it like the circle where this number should be the same as for the entire, like side to side, the whole barrel part?
Yes.
Just not the
Yeah.
ends?
Correct. Now, the enclosed charge. I know that this, which ends up being that, is equal to the enclosed charge divided by this constant. Well, my enclosed charge is, I have a uniform density here. I will use lambda to represent that linear charge density. It's just equal to charge over length. No matter what charge and length I pick, it's uniform, so that ratio stays the same. Well, I want to look, what is the charge inside my cylinder here, my Gaussian cylinder? Well, it's going to be that charge inside divided by the length. Linear charge density is just charge divided by length.
So lambda equals to is linear charge density.
Yes.
Wait,
Not in this context.
not
We've run out of letters. We only have 100 to deal with. So, my enclosed charge is just lambda L. So I have lambda L over epsilon sub naught equals